In this video, we'll take a look at section 24.3, which is curvilinear motion or motion in a plane in a two-dimensional area. The objective is to be able to find the rate of change of functions given in parametric form. So a quick review before we take a look at curvilinear. What we've worked with so far is rectilinear motion, that's straight line motion. So you're either moving in a straight line right to left, or you're moving in a straight line up and down. So that's rectilinear motion. Position is where you are in relation to where you started back and forth, either along the straight line, horizontal, or vertical. Remember that the velocity is the rate of change of displacement, and acceleration is the rate of change of velocity. Velocity is measured in feet per second, acceleration is measured in feet per second squared. So the types of problems that we've done before, if we had the equation for displacement, we would take the first derivative to find velocity, and then we would find acceleration by taking the second derivative. So just a quick example of what you've already done. If our position or displacement function, s equals 7t to the third minus 9t squared, what we want to do, that's given our displacement. We want to know how fast are we going, or what's our velocity at time equals 3, and what's the acceleration at time equals 3. So what we would do is take the first derivative of our function, substitute 3, and we would end up with 243 meters per second would be our velocity. Acceleration was taking the second derivative, substituting in 3, so our velocity is 108 meters per second per second. So what we want to do now is take that idea and apply it to curvilinear motion. We're not just moving backwards and forwards on a straight line. Now the motion of our object is in a plane, in a specified path, but not necessarily in a straight line. So some examples of curvilinear motion are trajectory, the path followed by a projectile, or the position of a projectile. Velocity and acceleration are both vectors. Now they have magnitude and direction. So magnitude is how fast, direction is in where are you going. All right, so equations for this position may be in parametric form. That means our x and our y coordinates are expressed in terms of a function t. The position with x and y coordinates expressed as functions in terms of time, and horizontal and vertical motions are considered separately, and t is the parameter, which is why we call it a parametric equation. So let's take a look at an example. So we have, if the horizontal distance x that an object is moved is given by x equals 3t squared, and the vertical distance y is given by 1 minus t squared, find the resultant velocity when t is equal to 2. So what does that function look like when x equals 3t squared and y equals 1 minus t squared? Well, you could think about substituting values for t, and that will give you values for x and y. So if we put in t equals 2, we get x is equal to 12 and y is equal to negative 3. And if we kept putting values in for time, at time 0, we would get this point, time 1, 2, etc. We would get this straight line. So the straight line represents that function in parametric form. And what the question is asking us, at 12, negative 3, or after 2 seconds, what we want to be able to find is the direction and the magnitude. So we want to find the length, or this vector right here, and then we also want to find the angle from horizontal. So what we end up with is we'll find a velocity vector x. We'll find out how fast our object is moving in the horizontal direction. Our vertical vector y, how fast our object is moving in the vertical direction. The resultant of those two is our velocity vector. So where this comes from, if you need to review vectors a little bit, is section 9.3 is vector addition by components. So if you're adding two vectors that are at right angles, the magnitude is the square root of your x component squared plus y component squared, and your reference angle is the inverse tangent of the absolute value of your y component divided by the x component. Okay, so that was chapter 9. So let's go ahead and take a look and solve the first question. So what do we do first? We find the x component of velocity and the y component of velocity. So we take our two functions that are written in terms of time and take the derivative of each. The derivative of x with respect to t would be 6t. The derivative of y with respect to t would be negative 2t. So these are the horizontal and vertical velocities. Now we evaluate at, in this case, t is equal to 2. So that means we substitute 2 into the derivative. So our Vx is 6 times 2, which is 12. And y component is equal to negative 2 times 2, which is negative 4. So we've got our x and our y component vectors, and now we want to add those together to get the resultant vector. So remember, when you're adding vectors together, let me just draw a quick picture. If your x is 12 and your y is negative 4, the resultant vector is the diagonal of that rectangle. Okay? So we basically, the formula comes from Pythagorean theorem. So the magnitude of the velocity is equal to the square root of your x component squared, so that would be 12 squared, plus your y component squared, negative 4 squared. So that would give us the square root of 144 plus 16, and that gives us approximately, rounded to the nearest tenth, 12.6. So 12.6 is our velocity. And it would be labeled, let's see if I have any, I don't have units, but the units would be units of distance per time. All right, now we want to determine the quadrant in which the resultant vector lies. So I'll take the picture from above. It lies here since x was positive and y is negative. It lands in the third quadrant. So what I want to find is that angle. So the reference angle is the velocity y vector, or is the result, is v sub y divided by v sub x. So that means the angle, reference angle, is the inverse tangent. So if I take the inverse tangent of negative 4, so that would be 4 over 12. The inverse tangent of 4 over 12, let me get the calculator. We want to go with degrees. Make sure you're in degrees. All right, and we are. So I want to find the inverse tangent of 4 divided by 12. And I end up with 18.4 degrees. So taking a look at this picture, the angle that I want is this angle right here. Notice we're rotating in the clockwise direction. So that angle of 18 degrees is going to be a negative 18.4 degrees. Okay, so that's our velocity. We are given our magnitude and our direction. All right, next example is going to be acceleration. We have the same situation. Let's see. Nope, a little bit different. So we want to find the magnitude and direction of the acceleration when t equals 2 for an object that's moving such that its x and y coordinates of position are given by the parametric equations. This time it's x equals t to the third and y equals 1 minus t squared. So this curve right here is the graph of the parametric equation. So if you were to take time values for time and substitute them, you would get x and y coordinates, and this curve is your function or your equation. And what we want to find when t equals 2, we would have this point right here. We want to know the acceleration. So we're going to find our horizontal and vertical vectors, and then we're going to find our position again. We're going to find our angle. So we're going to find the resultant vector, which is the diagonal of the rectangle, and then we're going to find the reference angle. All right, so here we go. Find the second derivative. So now this time, if x is equal to t cubed, the first derivative is dx dt, so that would be 3t squared. The second derivative is going to end up being our acceleration. 2 times 3 is 6t. The y component, my original, is 1 minus t squared. The first derivative, dy dt, is going to tell me velocity, vertical, negative 2t. Second derivative is going to tell me my acceleration, negative 2. So I've got my values, second derivatives for the x and the y component. Now the process follows what we did before. So now we take a look, find the x component at t equals 2. At t equals 2, the x component would be 6 times 2, which ends up being 12. And then the y component is a constant, negative 2, so it doesn't matter what t is, a sub y will always be negative 2. Now that gives us our x and y component acceleration. Now we can find the magnitude, the resultant. That's going to equal the square root of 12 squared plus negative 2 squared. This all looks so familiar, which equals 12.2. So that's the magnitude of acceleration. And then the angle is going to be, the reference angle is going to be the inverse tangent of the absolute value of the y component divided by x. So y component is going to be 2 over x component 12. So the inverse tangent of 2 over 12 is equal to 9.5 degrees. But we have to figure out from our picture, where is that from horizontal? And if you look at the diagram from horizontal, it's going down because we're in the third quadrant. So that's going to be a negative 9.5 degrees.